Welcome to the Explainer. Let's dive right in, shall we? Today, we're exploring the foundational geometric rules that literally construct the world around us. We're talking about the hidden, invisible framework that dictates everything from the screen you're looking at right now to the buildings you live in and even the roads you travel on. It's the rulebook of reality, parallel lines and transversals.
So here's our roadmap for today's explainer. We'll start with the parallel world, then meet the transversal. After that, we'll unpack congruent angle pairs and supplementary angle pairs before wrapping the whole thing up with real-world geometry.
Section 1, the parallel world, laying the foundation. Because before we start crossing lines, we really need to understand the lines themselves.
So, what does it actually mean for lines to be parallel? Well, the word itself comes from the ancient Greek word parallelos, which beautifully translates to side by side. Two lines are parallel if they sit on the exact same plane and maintain the exact same slope. This means they're perfectly equidistant at all times. They will absolutely never ever intersect, no matter how infinitely far they travel in either direction.
To ground this abstract geometry into everyday reality, just imagine two straight lines going side by side, perfectly spaced, exactly like a long stretch of train tracks. If those two rails ever got closer together or, say, drifted further apart, the train would derail. They literally have to maintain that exact distance forever, and that right there is the absolute essence of a parallel line.
Section 2, meet the transversal, crossing the tracks. All right, it's time to completely disrupt those perfect, infinite train tracks. We do that by introducing a new character, the transversal. Think of the transversal as a road cutting straight across our parallel train tracks. When this single line slashes through, it creates two distinct intersections, generating a total of 8 highly specific angles, numbered 1 through 8. This single crossing is the engine that powers a massive amount of geometric logic.
Now, before we compare the top intersection to the bottom one, let's look at a basic rule. Looking at just a single intersection, we find this fundamental truth. Vertically opposite angles are perfectly equal. When two lines cross, the angles directly facing each other, kind of like a mirror reflection across the vertex, they have the exact same measurement. Keep that in your back pocket because it's absolutely key to everything else we're about to see.
Section 3, congruent angle pairs, the geometry twins. Let's discover these geometry twins because when a transversal slices through parallel lines, it actually creates identical copies.
First, let's make sure we're absolutely crystal clear on our vocabulary here. You're going to hear mathematicians use the word congruent constantly. Congruent simply means the same, matching in size exactly. If we were to take a protractor and place it on two congruent angles, we'd get the exact same degree measurement right down to the decimal. And this brilliantly illustrates our first set of twins, corresponding angles. Notice how angles 1 and 5 are marked. They are in the exact same relative position at their respective intersections, the top right corner. You can visualize this as the F-shape rule. If you were to literally grab that top intersection and slide it straight down the transversal, angle 1 would sit perfectly on top of angle 5. They are completely congruent, no question about it. Let's move to our next set of twins and see how this builds, the alternate interior angle theorem, widely known as the Z rule. Here, we're looking at angles tucked inside the two parallel lines, making them interior, but on opposite sides of our transversal road, making them alternate. Notice angles 4 and 5. Because the lines are perfectly parallel, these opposite inside angles are perfectly equal twins. This Z-shaped logic flow is honestly one of the most powerful tools a mathematician uses for solving geometric proofs. So let's break down the mental steps. Step 1, trace the Z-shape along the parallel lines and the transversal. Step 2, confirm those top and bottom lines of the Z are actually parallel. Step 3, conclude with absolute certainty that the angles tucked inside the corners of that Z are exactly congruent. It works every single time, a real game changer.
Section 4, supplementary angle pairs, the straight line team. The crucial point here is that not all angles created by a transversal are identical twins. Some are teammates. And that brings us to our next set of mathematical rules.
Let's establish a clear contrast so you can easily lock this into your memory. On the left side of our mental rulebook, we have congruent angles. Those are our twins, perfectly equal in size. But on the right side, we have supplementary angles. Supplementary means these angles act as a team to create a straight line, which means together, their measurements will always add up to exactly 180 degrees.
And this brilliantly illustrates our teammates in action. Consecutive interior angles, also known as co-interior angles. You can remember this visually as the C-shape rule.
We're looking at angles inside the parallel lines, but this time on the same side of the transversal, like angles 3 and 5. Unlike the Z rule, these angles are not equal. Instead, they're supplementary teammates.
That magic number is 180. The math here is absolute and unavoidable. If that top consecutive interior angle is, let's say, 120 degrees, then the bottom angle inside that C shape absolutely must be 60 degrees. 120 plus 60 equals 180. If one angle gets smaller, the other must get larger by the exact same amount to maintain that 180-degree straight line team. It's like a geometric seesaw.
Section 5. Real-world geometry. Outside the classroom. We've gone through the rules, so let's zoom out a bit. Why should you care about corresponding angles or transversals?
Well, because these exact rules literally construct our physical and digital reality. In architecture and construction, buildings rely on parallel structural beams for basic integrity. The framing and roof construction act as transversals, distributing weight based on these exact angle rules. Look at road design. City grids are built on parallel roads sliced by crosswalk and avenue transversals. In mapmaking, lines of latitude and longitude form parallel systems intersected by transversals. Even in computer graphics and video game design, the engines rendering 3D environments calculate light and perspective using these exact geometric properties of parallel lines. It's the whole shebang.
All of this incredible, perfectly ordered geometry works flawlessly on a flat plane. It builds our cities and renders our digital worlds. But I want to leave you with a provocative thought to chew on. If everything we just learned relies entirely on perfectly flat, straight parallel lines, what happens to these rules when those lines have to travel across the vast, curved, spherical surface of the Earth? Can a true parallel line even exist on a sphere? That dives right into the wild world of non-Euclidean geometry, where the entire rulebook changes. Thank you so much for joining me on this geometric journey, and keep asking questions about the math that builds our world.